Let's look at this N curve. So this is another method to evaluate the noise margin. And this is typically used in the industry and for the testing, inline tester. So if you want to, let's say, characterize the wafer, let's say your chip, if you want to do the yield testing, so it's better to use this method because it's simpler to process the data. As you see earlier, for the butterfly curve, you have to draw the curve and then rotate, and somehow you get the maximum square. So it's not that straightforward. So this N-curve method is more straightforward. And also this N-curve method gives a critical current for the noise. So sometimes if you think the noise is in the form of current, then we want to know what is the maximum noise current you can tolerate in the SRAM cell. Because the butterfly curve only gives you the information of the voltage, right? You don't have the information of the current. Okay, so the N curve, this is because the curve is look like N, letter N, so that's why it's called an N curve. So the basic idea is that in the SRAM cell, you add a current source to the storage node, one of the storage node, for example, to this N2 node. And then you can, let's say, sweep the current and then measure the node voltage here. So you can get the relationship of the current I in versus this node voltage, if you think it's V in. And you can do that, then you can get this kind of N curve. So we can look at this N curve more closely. So here, initially, let's say if this is a rate condition, this stores 0. Now we change the example. Now on the right hand side is 0. Okay, N2 is 0. But you know it's the same thing. So let's say initially, if this node, if you don't have the current source here, so during the rate operation, we know that this node voltage will increase to some value. For example, if you don't have the current, that means the current is 0, okay? And then you get this crossing point here. This is the voltage that this node increased to. So due to the voltage dividing effect between those two, this voltage will increase to, for example, this 0.2 volts here. This is without the current source. Now if you add the current source, if the current source is initially if it's negative current, here negative current, so that means the current flow direction is really this direction, because we define the current, let's say, to be up. That means inject into the node. But if it's negative, that means we are extracting the current out from that node. Let's say the current is pointing down. If the current is pointing down, then you're going to discharge this node. So this node can be eventually discharged to 0 using the negative current here. So this is negative current, so you have this part of the curve if you measure that. Now you can switch to the positive current. Okay, positive current. So if you switch to the positive current, that means you are going to charge this node. If you charge this node, then the node voltage will increase above the 0.2 volts. Okay, that means it will increase. You charge, and it will increase till some point here. Then the flipping will happen. Because that node now is N2 node. Okay, basically the node stores 0. If that node voltage increases to a certain level, then we know you are going to trigger the flipping. It's like a write operation. So once you flip that, then you are going to have the snapback of the current. So this maximum current is defined as a critical current to disturb the state. So let's look at this in more detail. So this is as what I discussed. The point B, which is here, this is where you don't have the noise current here. This is in the normal operation. And this voltage here is defined by the beta ratio. If you have larger beta ratio, then you can move the point B towards the left, right? Because this is lower voltage. And then this P point is where the flipping will happen. And the point C is the metastable point. And then point D is the other stable point. So if this is still not obvious to you, then we can actually look at this curve. So those are 3 transistors, and pull up, pull down, and cascade. So you can actually look at the process when you sweep the current from negative to the positive. Then let's say you will go through the trace of A, B, P, C, D. Then the transistor current for each of them will go through this trace A, B, P, C, D, A, B, P, C, D for each of those transistors. And then you can draw them together in this plot. I know this is a little complicated, but if you do that, then the 3 colorful curves correspond to 3 transistors current. But as you notice that at any point along the voltage axis, at any point, if you add those transistor currents together, that will be the I in. Because at this node, you have current here, and current here. And according to the Kirchhoff law, you know, those 3 currents add up together will be the current for the I in here. So if you do that, for example here, if you do that, then you will, basically, if you add 4 of them together, including I in, if you add those 4 together, will be 0. Because all the current add up together will be 0. So you can use that to determine the black curve, which is N curve you need. Or if still this is too much complicated for you, then we can look at this curve. So this is what we draw the butterfly curve to get together with the N curve. Basically, those 2 are equivalent. Because here you see this is a butterfly curve, and we sweep the way in and get the way out. So we have this kind of butterfly curve during the read operation. And then let's say the voltage, look at the left axis. and the current corresponds to the right axis. So essentially, here, this flipping point is somewhere. This is a metastable point, correspond to the current crossing the zero here. And then here, when you start dropping the voltage, let's say the corner of this square will correspond to the maximum current here. And this one will correspond to the point here. So it's not just a one-to-one mapping between the butterfly curve and the N curve. So, I mean the N curve, if you look at this curve, it corresponds to the butterfly curve's one branch. The N curve corresponds to that. Any questions?
Yeah, why the largest current corresponds to the corner of the square?
So that's a good question. That's a good question. I don't have a good answer at this moment. And I think we have some reference for this N curve. You can check those papers and see if they talk about anything on that. So you can see that the N curve method is relatively newer, published in 2005 and 2006. But the original butterfly curve concept was published in 1987. Right? So this is a relatively new method.
Is that both of these two ways are also applied to other memories?
No, this is only for SRAM.
To characterize it?
Yeah, this is only for SRAM, because only SRAM will have this butterfly curve. So which one is better? Oh, as you see here, they are one-to-one mapped. So essentially they are equivalent. Okay. So just the different ways of the mapping. The butterfly curve is the relationship between the voltages, like the V1 and V2, or here this is VL and V right, V left and V right. That's two storage nodes. And the N curve relates to the current to the storage node, the noise current. So the butterfly curve directly relates to the noise between two nodes. It's more like the VT mismatch between the two nodes. But the N curve, as I said, is suitable for inline testing because you only need to sweep one time. You don't need to do this butterfly curve. You need to sweep two times. And then this N curve directly relates to the noise between the node and the ground because you are injecting the noise current, let's say, between the storage node and the ground. Previously, for the butterfly curve, if you recall previously, you are injecting the noise between those two nodes. And for the N curve, you are injecting the noise current between the storage node and the ground. So those are the differences. But essentially, they are the same thing. Those are static analysis.
Excuse me, Professor. What's the difference between these two kinds of noise?
So one is more related to the voltage noise. The other one is more related to the current noise. So this is the N curve, and we can see some real butterfly curve, measured data from the real chip. For example, this is the data from 65 nanometer CMOS SRAM, and here, for example, the nominal VDD may be 1.2 volts, and then if you, this is for read operation. So in order to get this curve, as we discussed earlier, you need to have those 3 transistors. If you do simulation, you have to do the spice simulation for those 3 transistors. If you do the measurement, then you have to bias the bit line to be a constant voltage and sweep the V1 and measure the V2. Okay. So if you do that, then you get this kind of butterfly curve, and then you can vary the VDD from 1.2 volts down to here like 0.8 volts, and then you will get the square for different VDD, and then you can plot the SNM as a function of the VDD. Of course, with smaller VDD, then the static noise margin will decrease, and it's about like 200 millivolts at 0.8 volts. So this is 65 nanometer, and this is 45 nanometer, and you can see the butterfly curve at different VDD. And this is 32 nanometer. This is high-k metal gate technology, and this shows both the butterfly curve and the N curve measured from this SRAM array. And then this is 22 nanometer. You see the noise margin already reduced below 200 millivolts. Previously, 65 nanometer, you see that the noise margin is still larger than 200 millivolts, right? But in this case, you can see that if your power supply is only, because for 22 nanometer, the typical power supply is like 0.8 volts. It's somewhere here. Then your noise margin is already below 200 millivolts. That means the scaling, will bring more challenges to the SRAM memory circuits design because of the shrink noise margin. If you plot different technology together on the same plot, you can see that with the scaling, the square becomes smaller and smaller. Of course, one major reason is the power supply, VDD, gets smaller with more advanced technology nodes. And later we are going to discuss that with the scaling, the other things, the variability will also increase. So we will talk about that point later. Let's say, so you see the challenges here in the scaling. So in the research community and also the industry, people come up with different techniques to improve the noise margin and improve the stability at more advanced technology nodes. And here are basically 2 kinds of approaches. The first approach is to modify supply voltage and also modify the pulsing sequence or the duration. So there are some examples, some reference papers here, different pulsing, dual supply, and so on. So basically, to modify the read and write operation protocol, like the pulsing sequence or the voltages. And the second approach is to add more transistor to the cell. So typically it's a 6 transistor SRAM cell. But if you want to improve the stability, then you can add one more transistor become 7T and 2 more transistors become 8T or even 10T. You can improve the stability, but of course at the penalty of larger area. So I think your homework has some. I'm not going to discuss those, okay, in class. So this is part of your homework. As I said, this is a graduate level course, and I hope that students can, do some literature survey and understand the latest technology trends by reading those research papers. So in your homework, you're going to read some of the papers about those advanced techniques, how to improve this stability by using those techniques. And one last slide before we end today's lecture. So this is the write static noise margin. So in the write operation, you can also define the noise margin. But it's a little bit different than the read. In the write operation, then those two transistors, let's say the two branches, the left-hand side and the right-hand side will be different, right? Because beta and beta bar will have different voltage. If you use that, then let's say, for example, this is this goes 0, and then this part will be the same as the read operation. So you have a similar kind of butterfly curve, this one branch. But the other one will be different. So you will not have the couple butterfly curve. You will end up with this kind of blue curve. And there's only one intersection of those two curves. That means you are going to write the data into this stable point. So you don't want to have any crossover of those two curves. That means your write is not defined. Your write direction is not defined. You want only one intersection. That means your write is definitely right to this data. So then the noise margin is defined as the minimal square between those two curves, because that is the distance between those two, and you don't want crossover. So that measures the noise during the write operation. So if you have any noise, then maybe you are going to write to the other stable point, which is not what you want. So then the minimal square between those two curves defines the write static noise margin. Okay, any questions? So if not, then we're going to end the lecture today here.